Yeah, it works this time. Okay, we can get started. Any questions about the homework first, and then maybe about the lecture in general?
Could we just go over like question one, both the questions, please?
Okay, and we see like question two also. So for today's homework, like first question is about a Poisson distribution. Basically, the Poisson distribution is when you take the limit when your sample size is relatively large and when your probability is relatively slow, and then you have a binomial distribution. Then you can approximate your binomial distribution to a Poisson distribution. Like for the coin flip example, that is like a very simple and standardized binomial distribution example because, for example, you're tossing like 100 times, right? You toss a coin 100 times, and then the probability of a head or a tail is both one half. So in this time, I think you should like mention in class like you have the mean, which is like n times p, and you have like standard deviation, which is a square root of mpq, etc. That is like some formulas for the binomial distribution, and you're going to use binomial distribution here no matter how large your sample size is. Like you toss 1,000 times, you toss a coin 10,000 times, like no matter how large your sample size are, you have to use a binomial distribution because the probability is not small enough, right? The probability of a head is a half. The probability of a tail is also a half. And in that case, if you like do some, some calculus, you do the limitation, um, uh, and it doesn't converge the Poisson distribution. However, if you both like two conditions, first you have a very large sample size, and second you have a very small probability, um, then you kind of uh, like satisfy the condition of a Poisson distribution. And in this question, the flying bomb hits. Um, it's exactly a Poisson distribution um, because first you have a relatively large sample size. I think you have 576 sectors, and then you have like a relatively small probability, right? So in this question, first you're gonna calculate lambda, and the parameter lambda in the Poisson distribution is um, n times p. Like you use a very large sample size n and multiplied by a relatively small probability p, and that gives you lambda. And the way to do this question is like first, because this chart like you have different k, you have different sectors. That's the only thing you have. And the way you're gonna do this is first you assume like the bombs are landing at random, following the Poisson distribution. That's your assumption. And using that assumption, you're gonna calculate the theoretical frequencies of k equals 0, k equals 1, k equals 2, like the theoretical assumption, like how many sectors um, would be bombed 0 time, how many sections would be bombed 1 times, how many sections would be bombed 2 times, etc. And then you compare your like theoretical sectors with like the reality, like you have the reality in this chart. Like in reality, 229 sector never been bombed, 211 sectors being bombed once, right? You have this the real world data, and then you compare your theoretical calculation to this real world data. And if those are close enough, and you would say, okay, my hypothesis actually stands because my hypothesized data matches the real world data. And if like those two differs by a lot, you would say your hypothesis doesn't stand. So the way to calculate, for example, the hypothesis frequency of k equals 2, you're going to use the formula, I think e to the minus lambda over k factorial times something. I have that one. I share this. I have shared this class slides. The probability of k, right, of k is a number of bumps, just equals to lambda to the k divided by k factorial times e to the negative lambda. You just plug in like k equals 0, k equals 1, k equals 2 from that chart, and you get your like theoretical probability. And you use that theoretical probability multiplied by the number of sectors, 576, you get your theoretical sectors. And last step is you compare your theoretical sectors with the real world data. If those two are close enough, you would say your hypothesis stands. That's how you're gonna do this question. Any questions about it? If the two are close enough, you would say your hypothesis actually stands, because at first you don't have any, like I didn't tell you this comes from a Poisson distribution. I just gave you like what happens in reality. I gave you that chart. That's what happens in reality. And you're gonna test if the bombs are landing at random, which means if the bombs are landing at random, they follow the Poisson distribution because of just what I said. You have a very large sample size at very small probability. So if the bombs are land at random, it follows the Poisson distribution. And you just first you assume the bombs are landing at random. And that means you assume this process follows the Poisson distribution, and you can use the conclusion from the Poisson distribution, like the formula I just showed on the screen, and you can calculate your theoretical probability, your theoretical frequency. And then if your theoretical frequency is very close to what really happens in real life, you would say, okay, my hypothesis actually stands, which means your hypothesis is the bombs are landing at random, and that stands. And you're gonna conclude, okay, those bombs were actually landing at random. That's how to do it. Okay, for question 2, I just talk about question 2 very, yeah, if it's close, it's landing at random. Like basically this, like we didn't, okay, so I think I should spend more time on this, right? We didn't talk about like hypothesis testing yet. I think from lecture or like whatever, we didn't do the hypothesis testing, but basically you are practicing this every day. But like maybe you didn't notice it. For example, I claim I have $2 million. Let's say I claim I have $20 million in my bank account. And what you're gonna say is you're gonna say no way, it's impossible, right? And the way you analyze this question is first you're gonna assume, okay, your TA really has $20 million in his bank account. And then you're gonna find some evidence against it. If you find enough evidence against it, you're gonna reject your hypothesis. This is how it works. So maybe you would say your TA looks like 22 years old, very less likely to have that much money, plus he's still attending school, a reasonable person if he has like $20 million overnight, he would probably drop out from school, right? And you have some other reasons, and those reasons makes you less believe that I actually have $20 million. You cannot reject me 100%, but you would say the probability that that guy had $20 million is very low. The probability is very low. So in real life, you don't say like, Victor, the probability that you had $20 million is very low. You said, Victor, you're joking, right? That's how you say that, because it's also like the idea in statistics. In statistics, there's a cutoff of 5%. So you're kind of using that. You're kind of using that in real life. Like when you find the probability is less than 5%, in statistics world, you reject the null hypothesis. In real world, you just say it's impossible, you're telling a lie. That's how it works. So basically you're practicing that every day. And for this question, you're kind of using the same idea. First, you assume the bombs are landing at random. You assume it is a Poisson distribution. And then you're gonna find some evidence against it, right? What kind of evidence is the evidence against it, right? In this case is when you use the Poisson distribution and calculate the hypothesis, like hypothetical frequency, and you find it differs a lot from what happens in real life. And that is actually the evidence against your null hypothesis, against your assumption. But if your hypothetical data is actually very close to what happens in real life, then you cannot find enough evidence to overturn your hypothesis, to overturn your assumption. And so here you don't have a very rigorous proof, like 5% or something. But the idea is, if you really think your hypothetical frequency is very close to what happens in real life, then you don't have enough evidence to reject your assumption, and that's how it works. I think you're gonna learn some hypothesis testing very soon, and that's the basic logic of hypothesis testing. And I just use like I think a stupid example to show you, like you actually use it every day. Maybe you didn't notice it. So I think that's enough for the first question. I just continue to the second one. So the idea of this question, like I don't expect any like rigorous proof of this question, but the idea is, like if your distribution follows like a general formula, like e to the lambda t or e to the minus lambda t, then it follows the exponential distribution. And here you have two atoms. Those two atoms are very importantly, they are independent of each other. Like what happens to the first atom doesn't really affect the second atoms. Like the second atoms, whether it disintegration or not, only depends on time. right? It only depends on itself. It has nothing to do with the first item. So basically, the two are independent, and uh, there's a very like important conclusion. Like if A and B are two independent events, then the probability of A intersect B is just equal to the probability of A times the probability of B. That's a very important conclusion of independence. And in this case, from like some physical intuition, or you just assume like those two atoms are independent, then the probability of um, like both of them disintegration is just the probability of the first one disintegration times the probability of second one disintegration. So what you're gonna have is you have something like e to the minus lambda t times e to the minus lambda t. You're gonna have something like that. And if you remember, like e to the a times e to the b is just equal to e to the power of a plus b, right? So in this case, you just need to plus like what's in the exponential power, right? And you have like minus lambda t plus minus lambda t, and that gives you like minus 2 lambda t, and you can build that into like one parameter. So that's again an exponential distribution with parameter 2 lambda. That's the idea, right? You're gonna like form your writing or form your logic like a little bit more clearly. But the idea is basically e to the a times e to the b equals e to the a plus b. That's the idea of this question. Any question about that? Okay, if you start like I think like homework for this week is kind of simple. Like you only have like 2 questions, but for next week, it's relatively tough. I think the homework for next week is probably the most difficult one through the whole semester. So you're gonna, I think you should plan to like leave more time for that. And if you have already started and have some questions, you could also ask in this session. I could discuss about them like like relatively basic way. I didn't look through the question, but I can tell you about like the idea of the question. But if not, I'll still talk about them like next Thursday. I think it's due next Thursday, right? Yeah, it's due next Thursday. Okay, see you next Thursday. Bye. Bye, have a good one.